Welcome to part 2 of chapter 6. Okay, we're going to continue our discussion about jointly distributed random variables. But then in this case, we're going to delve into a little bit more about, well, if I have multiple independent random variables, how can I work out their sum? Okay, and also we're going to look at the conditional distributions for the discrete and continuous case. Okay, so we're going to start with the sums of independent random variables. Okay. So here, okay, if you have a joint density, okay, x and y, so remember now we are working with sum of 2, okay, and then we're working with the joint PDF of x and y here, okay. Then there is a really handy result, which as you can see involves going over a little bit more of the calculus. So in practice, you do still need to do integration, okay, but it is pretty handy here. I think these two results that you're able to use. Okay, so if you have x and y having a joint density fxy, then the sum, okay, the sum of a new random variable. Okay, so we're using x plus y, okay, in the subscript. Okay, and then we're talking about like any value of z. Okay, so this is the PDF at that point. And what this does, there's two versions of it, whichever you can do, I guess, depending on the question, is that you can either, okay, do a single integral with respect to x, okay? So you're still gonna have the joint PDF as you have, okay? But then here, okay, you still keep x, okay? But then you replace y with z minus x, okay? Because the sum, okay? So you can think of this as small x plus small y equals to small z, right? So that's the same as saying small y equals to z minus x. Okay, so pretty much we're replacing, okay, y in terms of z and x, okay, but in particular, if you notice that like we're getting rid of y, okay, we're replacing or re-expressing y in terms of what we're integrating with, okay, which is x, okay, and also the new random variable z, okay. So another way you might have seen this is like trying to write like capital Z equals to x plus y, okay, and then z is the new random variable that we're working with, so you could have z and x in this new integration, okay. So imagine if we keep doing this integration, x is going to be integrated out, right? So whatever here is going to be left anything like everything about z, okay. You have no y anymore, no x anymore after you do the integration, okay. So similarly, okay, we have a similar argument down here if you want to do dy, okay, so that's equivalent of replacing or re-expressing x in terms of z minus y, okay? And then you're doing the integration with respect to y. So what this remains is, again, going to be a function about z, okay? So if I write it generically, it's going to be a function about z, okay? And then z is the random variable, right? So we're good. So this is the generic result, okay? And for us, for this section, we focus on when x and y are independent, then you can use this further formula, okay? So when they're independent, as you can imagine, the joint, okay, so let me maybe clear here, okay? So for the first one, okay, so the first one we're doing is being further expressed in this way, okay? So let's focus on this too for now, okay? So we're still doing dx, okay? So essentially, we're breaking the joint of x and in this case z, but then really still x and y, okay? And so down here, we know that if x and y are independent, okay, we know from before that their joint PDF becomes the product of the marginal PDF, okay? So what you can do is instead of writing the joint as x and z minus x, okay, we're writing the product of the margin of fx at x and then fy at z minus x. Okay, so we still use this y because, well, as you can imagine, this kind of questions, you're given what y is, okay, but you're evaluating at z minus x, okay. So at the end of the day, the random variable involved in this particular case will still be about x and z, okay, and then once you integrate out x, you're going to be left with z, okay. And similarly, we have this comparison, okay, for the second case, okay. So we call this convolution formula, okay. Mostly because, well, now we're able to break the joint into the product of the marginal due to independence. And because of that, you can further express what you want to do. Okay, so again, I think this will become a little bit more clear, okay, when we start to do exercises, but the method itself works in this way generically. Okay, So as you might be wondering, okay, if you are having a CDF, okay, the sum, okay, the CDF of the sum of x plus y, then it is also called the convolution of the distributions of the CDF of x and CDF of y. Okay, so as you can imagine, well, we can always, when both of them are continuous, we can always work back and forth, right, between small f and capital F. From small f to capital F, we do integration, right? From capital F to small f, we're doing differentiation, okay? So we bring this up because we do want to show you why it works, okay? We show you the formula, but then let's talk about it to see why the formula that we're showing above is working, okay? So the argument that I'm giving here is just very generic. We're not assuming x and y are independent, but I want to direct you to the textbook page 239. It gives a derivation when x and y are independent, okay? So I highly recommend you check it out. Here, the argument or like the derivation we're showing is more about when they're like no requirement of their being dependent, and just to give you the way to think about this type of problem, okay? So, all right, so just like when we are trying to figure out like the PDF of a function of a random variable, where if the formula cannot be used, we can always go back to the definition of the CDF and then take the first order derivative to get the PDF, okay? So this is what we're trying to do, okay? So if you imagine, okay, this particular CDF, okay, the sum of x and y, okay, evaluate as z, okay? And we know that, well, this is equivalent, right, to doing a double integral of the joint of x and y, okay, within this particular range, okay? So remember, this is what? This is trying to express the probability of x plus y, right, all capital letter, but then small or equal to small letter z, okay? And this, just like what we're talking about for part 1 of chapter 6, this is actually a probability integration exercise, right? Like we know that this is a particular region that we need to integrate over in order to get this probability, and that translate, right, into a double integral, okay? And then as we know, the next step is trying to figure out the bounds, okay? So for us, just for illustration, let's do dy dx, okay? And then when we do dy dx, okay, so x generically, so the outer one, right? The outer one is always the absolute bounds, whatever we can get. In this case, it's generic. We don't know about specific bounds, so it's negative infinity to positive infinity. That's on the real line, okay? And then if you think about the bounds of y, this is another exercise, I guess, for that bounds calculation. We know that y is on the real line, right? So the smallest you can get is negative infinity, okay? But the upper bound in this case, okay, because it's now related to x, right? And then we know that x plus y can never be greater or equal to z, okay? So the upper bounds now become z minus x, okay? So this is generic x and y, they do not need to be independent, and we're merely using the definition of the CDF and then turn it into a double integral for the joint PDF and then work out the bounds. So the next step, as you know, right, if we want to get the PDF from the CDF, we need to take the first order derivative, in this case with respect to z, okay, because z is the random variable, okay? So this part, okay, is can be done in this way, okay? So if you look at, so let me clear, okay, and then go again, okay? If I look at this part, okay, and I'm doing a double integral, right? And then once we do that, we need to take the first order derivative with respect to z, okay? So let's see where z happens. Z only appears here, okay? So the outer integral, the parts about x, okay, is actually like a constant, right, in terms of z. So what we're doing, so we can bring this differentiation sign into the middle one, okay, because that's where z is about, okay? And when you do it, okay, so this is the part I think it's a little bit hard to understand, but if you go to the textbook to look at the case where x and y are independent, you can actually break it down, right, into the product of the marginal and then go from there, okay? But once you do that, and then here, I just want to talk about the big idea here, is that if you're able to do it, even if they're not independent, once you do that, you can figure it out that the joint, okay, of x and y, actually, so this, let me put it this way, once you do the integration here and then take the first order derivative, you can imagine that when you're doing the integration, right, it's integrating with respect to y, right? So you're working with the second random variable over here, okay? And then you take the first order derivative with respect to z, which, as you can see, we used to have the joint, right, of x and y, where y is being integrated out, okay? And then we're taking the first order derivative with respect to z, where z is z minus x, right? So when you're using chain rule, that becomes 1 as well. So that's why you are left just with the joint fx y, and then with x equals to like small x and z minus x. Okay, so again, in this video, I'm trying to give you the overview, or like a high level overview of how things are done. But if you check out the textbook, again, highly recommend when you're able to see that x and y are independent, you can actually break this whole thing down into the product. And then when you do integration, when you do differentiation, I think it becomes easier to do. Okay, so definitely check that out. And yeah, and let me know whenever you have questions.